The universe is a vast expanse, filled with billions of stars, galaxies, and planets. Yet for all our advances in science and technology, it remains shrouded in mystery. From the swirling depths of black holes to unsolved signals received from outer space to the unseen mysteries of the Great Attractor, the cosmos is full of phenomena that defy our understanding. Even as we send probes to distant worlds and gaze through powerful telescopes, we find ourselves confronting questions that seem to deepen with every new discovery. What lies beyond the event horizon of a black hole? Could there be a hidden ninth planet lurking in the distant reaches of our solar system? Why do some galaxies seem to vanish without a trace? Join me as we uncover these mysteries. Anomalous signals. In the vast expanse of the universe, among the countless stars and galaxies, there are signals that have sparked the curiosity of scientists and enthusiasts alike. These signals, brief yet powerful, seem to call out from the unknown, challenging our understanding of the cosmos. One of the most famous of these signals is the WOW signal, detected in 1977, while others, known as fast radio bursts or FRBs, continue to puzzle researchers to this day. It was a warm summer evening on August 15, 1977, when a radio telescope at Ohio State University, affectionately known as the Big Ear, picked up something extraordinary. This telescope, part of a long-term project searching for extraterrestrial intelligence, was quietly scanning the skies, listening to the faint whispers of the universe. For the most part, it had only heard the usual noise of space, the hum of cosmic background radiation, and the occasional distant pulsar. But on that night, for a fleeting 72 seconds, the Big Ear heard something different, something unexplainable. The signal came from the direction of the constellation Sagittarius. It was strong, much stronger than the usual background noise, and it had a very specific frequency. It was so remarkable that when Jerry Ehrman, the astronomer who discovered it, saw the data, he circled it on the printout and wrote one word in the margin: WOW. The name stuck, and the signal became famously known as the WOW signal. What made this signal so intriguing was not just its strength or the fact that it was so brief, but its exact frequency. The signal was at 1420 MHz, the natural emission frequency of hydrogen, the most common element in the universe. Some scientists have speculated that if an intelligent civilization wanted to send a signal across the vast distances of space, they might choose this frequency, knowing it would stand out among the cosmic noise. Despite its tantalizing nature, the WOW signal has never been detected again. Over the years, numerous attempts have been made to find it, but all have come up empty. Theories abound about what could have caused it. Was it a signal from a distant alien civilization trying to make contact? Or perhaps it was some unknown natural phenomenon, or maybe even a signal from Earth reflected off space debris. But none of these theories have ever been proven. And the WOW signal remains a cosmic mystery, an unsolved puzzle that continues to captivate the imagination of those who search the skies. While the WOW signal stands as a singular event, the universe has provided us with other strange signals that are no less mysterious. In recent years, astronomers have detected what are known as fast radio bursts, or FRBs. These are incredibly intense bursts of radio waves that last only a few milliseconds. They seem to come from all over the sky, from deep in space, far beyond our galaxy. The first of these FRBs was discovered in 2007, buried in archival data from a radio survey of the sky. At first, scientists were skeptical, thinking it might be some kind of interference or an error in the data. But as more and more FRBs were detected, it became clear that these signals were real and that they were coming from the far reaches of the universe. One of the most intriguing aspects of FRBs is their sheer power. In just a few milliseconds, an FRB can release as much energy as the sun does in an entire day. But what could be causing these bursts? That question has led to a wide range of theories, some grounded in known physics, others more speculative. Some scientists believe that FRBs might be caused by magnetars, a type of neutron star with an incredibly strong magnetic field. As these stars rotate, their magnetic fields could interact with surrounding material in such a way that it produces these intense bursts of radio waves. Others suggest that FRBs could be the result of two neutron stars colliding, or perhaps a black hole devouring a neutron star. But there are also those who wonder if FRBs might be signals from an advanced alien civilization. After all, if we were to try to communicate across the vast distances of space, we might use powerful bursts of energy that could travel for billions of light years. Some even speculate that FRBs could be the exhaust from enormous spacecrafts, harnessing energy from stars to propel themselves through the cosmos. Yet, despite all these theories, the true origin of FRBs remains unknown. What we do know is that they are incredibly distant, some coming from billions of light years away, and that they are happening all the time. Dozens of FRBs have been detected so far, and new ones are being discovered regularly. A few of these bursts have even been seen to repeat, flaring up again and again from the same part of the sky, adding another layer of mystery to an already puzzling phenomenon. The search to understand FRBs is ongoing, with astronomers around the world using increasingly sophisticated technology to try and pin down their sources. Each new discovery adds a piece to the puzzle, but it also raises more questions. What is causing these bursts? Why do some repeat while others do not? And what does it mean that we are just now beginning to notice these signals in a universe that has been around for billions of years, like the WOW signal before them? FRBs challenge our understanding of the universe. They remind us that, despite all we have learned, there is still so much we do not know. Dark secrets of the universe. In the quiet darkness of space, where the light of distant stars flickers faintly, lies a profound mystery. For all the wonders we have uncovered about the universe, there is something that eludes our grasp, something that holds the cosmos together, yet remains invisible, undetectable by any means known to us. This unseen force is what scientists call dark matter, and its presence is felt more than it is seen. It whispers to us through the motions of galaxies, bending the fabric of space and time, hinting at a deeper hidden structure to the universe. In the early 20th century, as astronomers began to study galaxies in more detail, they noticed something puzzling. The stars at the edges of galaxies were moving much faster than they should have been, according to the laws of physics. Based on what we know about gravity, the farther a star is from the center of a galaxy, the slower it should move, much like the planets in our solar system. Yet, observations showed that stars at the edges of galaxies were moving at nearly the same speed as those closer to the center. This strange phenomenon, observed in galaxy after galaxy, could not be explained by the visible matter alone. This anomaly in galactic rotation curves led scientists to a bold hypothesis. There must be some kind of unseen matter exerting a gravitational pull on these stars, keeping them in their fast orbits. This matter, whatever it was, did not emit light, did not interact with electromagnetic forces, and could not be seen directly. It was dubbed dark matter, a mysterious substance that seemed to make up the majority of the mass in galaxies, and yet remained completely hidden from view. The idea of dark matter was further supported by the behavior of galaxy clusters, where the gravitational pull needed to keep the clusters from flying apart was far greater than could be accounted for by the visible matter alone. Something else had to be there, something massive and invisible, binding these galaxies together. But what is dark matter? Despite decades of research, we still do not know. Scientists have proposed various candidates, from weakly interacting massive particles, or WIMPs, to exotic forms of matter that do not interact with light. But so far, dark matter has evaded detection, remaining one of the greatest unsolved mysteries in physics. Dark matter is not just an enigma. It plays a crucial role in the formation and structure of the universe. Without dark matter, galaxies as we know them might never have formed. In the early universe, dark matter would have acted as a kind of cosmic scaffolding, pulling together clouds of gas and dust, which eventually formed stars and galaxies. Its gravitational influence shaped the large-scale structure of the universe, forming the vast cosmic web of filaments and voids that we see today. As scientists continue to search for dark matter, they're also grappling with another profound mystery, one that has even more far-reaching implications for the fate of the universe. This mystery is known as dark energy, and it is the force driving the accelerated expansion of the universe. In the 1990s, astronomers studying distant supernovae made a shocking discovery. They found that the universe was not just expanding, as had been known since the time of Edwin Hubble, but that this expansion was speeding up. This was completely unexpected. According to the laws of gravity, the expansion of the universe should be slowing down over time, as the pull of gravity tries to bring everything back together. But instead, these distant supernovae were dimmer than they should have been, indicating that they were farther away than expected. The only explanation was that the expansion of the universe was accelerating. This acceleration could only be explained by some unknown force or energy, something that counteracts gravity on cosmic scales. This force was named dark energy, a mysterious and pervasive energy that makes up about 68% of the total energy content of the universe. Unlike dark matter, which pulls things together through gravity, dark energy seems to do the opposite, pushing the universe apart, driving galaxies away from each other at an ever-increasing rate. The nature of dark energy is one of the biggest questions in cosmology today. Some theories suggest that dark energy might be related to the energy of empty space, also known as the vacuum energy, which could have a repulsive effect on the universe. Others propose that dark energy could be a new, unknown field that permeates all of space, or that it might signal a fundamental change in our understanding of gravity and the laws of physics. The discovery of dark energy has profound implications for the future of the universe. If the expansion continues to accelerate, it could lead to a scenario known as the Big Freeze, where galaxies move so far apart that they become isolated in the vast emptiness of space. Over time, stars would burn out, and the universe would grow cold and dark, a place where nothing new could form, a universe in perpetual twilight. Yet despite these ominous predictions, dark energy also holds the key to understanding the ultimate fate of the cosmos. Will the expansion continue forever, or will it eventually reverse, leading to a big crunch where the universe collapses back in on itself? Or is there a possibility of some other outcome, something beyond our current understanding? As we peer deeper into the universe, using ever more powerful telescopes and detectors, we are slowly beginning to unravel these dark secrets. The study of dark matter and dark energy has transformed our understanding of the cosmos, revealing a universe far stranger and more complex than we ever imagined. These hidden forces, invisible yet all-pervasive, shape the destiny of galaxies, the fate of the universe, and perhaps our place within it. The Big Bang and cosmic inflation. In the beginning, there was nothing as we know it. No stars, no galaxies, no light, and no time. But about 13.8 billion years ago, something extraordinary happened. From a point smaller than an atom, the universe as we know it began to expand. This event, known as the Big Bang, marks the birth of everything that exists, every star, every planet, every particle of matter and energy. The universe began as an almost unimaginably hot and dense state, and in a fraction of a second, it expanded at an incredible rate. This moment of rapid expansion is what scientists refer to as cosmic inflation. Cosmic inflation is one of the most critical yet mysterious events in the history of the universe. It happened in the first tiny fraction of a second after the Big Bang, during a time so brief that it almost defies comprehension. During inflation, the universe expanded exponentially, growing from subatomic scales to something the size of a grapefruit in an instant. This expansion was not just rapid, it was faster than the speed of light. Inflation stretched the very fabric of space itself, smoothing out any irregularities and setting the stage for the formation of the galaxies and stars we see today. The theory of cosmic inflation was proposed in the early 1980s by physicist Alan Guth, who sought to explain some puzzling aspects of the universe that the Big Bang theory alone could not address. One of these puzzles was the uniformity of the universe. No matter where we look, the universe appears to be remarkably similar in all directions, with the same temperature and structure. This observation was difficult to explain because, according to the Big Bang theory, different regions of the universe should have been too far apart to have any influence on each other. Inflation solves this problem by suggesting that the universe was once much smaller and more connected. During inflation, these small regions were stretched out so rapidly that they now appear as separate, uniform parts of the universe. This rapid expansion also explains why the universe is so flat, another feature that puzzled scientists. Without inflation, the universe should have more curvature, but inflation stretched it out so much that it became nearly flat, like a stretched rubber sheet. Yet even with the success of the inflationary model, many questions remain. What caused inflation? What was the universe like before inflation? These are mysteries that scientists are still trying to unravel. While the evidence for inflation is compelling, particularly the patterns in the cosmic microwave background radiation, the afterglow of the Big Bang, much about this early phase of the universe's history remains unknown. The study of cosmic inflation continues to be one of the most active areas of research in cosmology, as scientists strive to understand the forces that shape the universe in its very first moments. As the universe expanded and cooled after the Big Bang and inflation, matter began to form. The first particles emerged from the hot, dense plasma, eventually coalescing into atoms, which later formed stars, galaxies, and all the structures we observe today. But as scientists began to take inventory of the universe, they encountered a perplexing problem. The amount of normal matter, matter made up of protons, neutrons, and electrons, also known as baryonic matter, did not add up. This discrepancy is known as the missing baryons problem. According to cosmological models and the theory of nucleosynthesis, which describes how the first elements were formed in the early universe, there should be a certain amount of baryonic matter present in the universe. However, when astronomers count up all the stars, galaxies, and gas in the observable universe, they find only about half of the expected amount. The rest of the baryons seem to be missing, hidden somewhere in the vastness of space. For years, this missing baryon problem puzzled scientists. If half of the normal matter in the universe was unaccounted for, where could it be hiding? The answer, it turns out, might be in the vast spaces between galaxies, in what is known as the warm-hot intergalactic medium, or WIM. This WIM is thought to be a diffuse, thread-like network of gas that stretches between galaxies, forming part of the cosmic web that connects everything in the universe. The WIM is incredibly difficult to detect because it is so diffuse and faint, but recent observations have started to reveal its presence. Using powerful X-ray telescopes, astronomers have been able to detect the faint signatures of this gas as it absorbs X-rays from distant sources. These observations suggest that much of the missing baryons may be hiding in this intergalactic medium, spread out over vast distances, far from the bright lights of stars and galaxies. Even as we begin to solve the mystery of the missing baryons, it raises new questions about how this matter interacts with the rest of the universe. How does the WIM influence galaxy formation and evolution? What role does it play in the large-scale structure of the universe? And why did so much of the universe's normal matter end up in these faint, distant regions? These are questions that scientists are only beginning to explore as they continue to map the hidden matter of the cosmos. The quantum realm. Beyond the reach of ordinary observation lies a world so strange and mysterious that it defies our everyday understanding of reality. This is the quantum realm, a domain where the rules of physics as we know them break down, and where particles can exist in multiple states at once, appear out of nowhere, and influence each other instantly across vast distances. It is a place where certainty gives way to probability, and where the very nature of existence is blurred and uncertain. One of the most intriguing concepts in the quantum realm is the idea of quantum foam. Quantum foam refers to the idea that at the smallest scales, much smaller than atoms or even subatomic particles, space-time itself is not smooth and continuous, but rather a frothy, chaotic sea of activity. This idea comes from the work of physicist John Wheeler, who suggested that at the Planck scale, the smallest scale of length in the universe, space-time might be bubbling and fluctuating wildly. In this quantum foam, particles and antiparticles could spontaneously pop in and out of existence, appearing for just a fleeting moment before annihilating each other. These fluctuations are a consequence of the Heisenberg uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be precisely known at the same time. In the quantum foam, uncertainty reigns supreme, and the very structure of spacetime is constantly shifting and changing. This chaotic nature of quantum foam has profound implications for our understanding of the universe. It suggests that spacetime is not a static, unchanging backdrop against which events unfold, but rather a dynamic, ever-changing fabric that is constantly being reshaped by the quantum processes occurring within it. At these scales, the smooth, predictable world of classical physics gives way to a world of probabilities and possibilities, where the laws of nature are not fixed, but fluid and flexible. The concept of quantum foam also raises questions about the nature of gravity and the fundamental forces of the universe. If space-time is subject to such wild fluctuations at the smallest scales, what does this mean for our understanding of gravity, which is traditionally described as a smooth, continuous force? Some physicists believe that exploring the quantum realm could lead to a deeper understanding of gravity, and perhaps even to a unified theory of quantum gravity that could reconcile the seemingly incompatible theories of quantum mechanics and general relativity. One of the most fascinating and challenging aspects of the quantum realm is how it relates to black holes, those enigmatic objects that warp space-time to the point where nothing, not even light, can escape their gravitational pull. Black holes are regions of space where gravity is so intense that the normal laws of physics break down, creating a singularity, a point of infinite density where space-time itself is torn apart. For many years, black holes were thought to be completely black, emitting no radiation or energy of any kind. But in the 1970s, physicist Stephen Hawking proposed a groundbreaking idea. Black holes might not be entirely black after all. According to Hawking's theory, black holes should emit a very faint form of radiation, now known as Hawking radiation, due to quantum effects near the event horizon, the boundary beyond which nothing can escape the black hole's grasp. Hawking radiation arises from the quantum foam that surrounds the black hole. As virtual particles pop in and out of existence near the event horizon, one of these particles can be captured by the black hole, while the other escapes into space. This process results in the black hole losing a tiny amount of mass. And over an incredibly long period of time, this slow leak of energy could eventually cause the black hole to evaporate completely. The concept of Hawking radiation was revolutionary because it suggested that black holes are not eternal, as previously thought, but that they could slowly evaporate over time, losing mass and eventually disappearing. This idea also raised new questions about the nature of information in the universe. According to the laws of quantum mechanics, information about the state of a system should never be lost. But if a black hole evaporates completely, what happens to the information that fell into it? This paradox, known as the black hole information paradox, remains one of the most profound puzzles in theoretical physics. Despite its theoretical importance, Hawking radiation has never been directly observed. The reason is that the radiation is extremely weak, far weaker than any other form of radiation in the universe, making it incredibly difficult to detect. The temperature of Hawking radiation is lower than the temperature of the cosmic microwave background, the faint glow left over from the Big Bang, which means that it would be almost impossible to observe this radiation from any black hole that exists today. Nevertheless, the idea of Hawking radiation has inspired countless studies and experiments, as scientists strive to find ways to detect it and to understand its implications for the nature of black holes and the universe itself. Some researchers have suggested that if we could create tiny microscopic black holes in the lab, perhaps using powerful particle accelerators, we might be able to observe Hawking radiation directly. Others are exploring the possibility that primordial black holes, formed in the early universe, could still exist today, and that they might be small enough to be emitting detectable amounts of Hawking radiation. The quantum realm, with its strange and unpredictable nature, challenges our understanding of the universe at its most fundamental level. Unseen forces. As we observe the cosmos, we find that it is not just the stars, galaxies, and dark matter that shape its structure, but also forces and phenomena that remain largely unseen and not fully understood. Among these are the Great Attractor and cosmic voids, two contrasting features of the universe that challenge our understanding of gravity and the large-scale structure of the cosmos. Additionally, there are the ultra-high energy cosmic rays that travel through space, defying the limits of known physics and hinting at forces and events that are still shrouded in mystery. In the 1980s, astronomers studying the motion of galaxies noticed something peculiar. As they mapped the movements of galaxies in the local universe, they discovered that many of them, including our own Milky Way, were moving towards a particular region of space at a significant speed, about 600 kilometers per second. This region, located in the direction of the constellation Centaurus, became known as the Great Attractor. The Great Attractor is not a single object like a star or a galaxy, but rather a gravitational anomaly, a region of space where the pull of gravity is unusually strong. This immense gravitational force appears to be drawing galaxies toward it, causing them to cluster together in that part of the universe. However, when astronomers tried to pinpoint the exact source of this gravitational pull, they encountered a problem. The Great Attractor lies in a region of the sky known as the Zone of Avoidance, an area obscured by the dense dust and stars of the Milky Way, making it difficult to observe directly. Despite this, observations using X-rays and other wavelengths have provided some clues. It appears that the Great Attractor is part of a much larger structure called the Laniakea supercluster, a vast network of galaxies that includes our own. The Great Attractor may be a region where several galaxy clusters are converging, creating a gravitational hotspot that pulls in galaxies from hundreds of millions of light-years away. Yet even with this understanding, the exact nature of the Great Attractor remains a mystery. Is it a massive cluster of dark matter? A supercluster of galaxies that we have yet to fully see? Or is it part of an even larger structure that we do not yet comprehend? These questions continue to drive research as astronomers attempt to map out the large-scale structure of the universe and understand the forces that shape it. In contrast to the Great Attractor, which pulls galaxies together, there are also vast regions of space that seem almost completely empty. These are known as cosmic voids, immense dark areas where few galaxies exist, and the density of matter is far lower than in other parts of the universe. Cosmic voids are some of the largest structures in the cosmos, spanning hundreds of millions of light-years across. The existence of these voids was first hinted at in the 1970s and 1980s, when astronomers began to create three-dimensional maps of galaxy distributions. They found that galaxies tend to form along thin filaments and walls, creating a web-like structure, with large empty spaces in between. These empty spaces are the cosmic voids, regions where gravity has not pulled matter together to to form galaxies and stars. The study of cosmic voids provides insight into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. In these voids, where the effects of gravity are weaker, the influence of dark energy may be more pronounced, pushing the walls of the voids apart and making them even larger. By studying the shape, size, and distribution of voids, astronomers hope to learn more about dark energy and its role in the evolution of the universe. However, the voids themselves are not completely empty. They contain a faint, diffuse gas, and in some cases, small, isolated galaxies that seem to have drifted away from the larger cosmic structures. These lonely galaxies are of particular interest to scientists, as they may offer clues about the formation and evolution of galaxies in environments very different from those we typically observe. While the large-scale structure of the universe presents mysteries of its own, there are also puzzling phenomena on a much smaller scale that challenge our understanding of physics. One of these is the mystery of ultra-high energy cosmic rays, particles from space that strike the Earth with energies far greater than anything we can produce in our most powerful particle accelerators. Cosmic rays are high-energy particles, mostly protons, that travel through space at nearly the speed of light. When they collide with atoms in the Earth's atmosphere, they create showers of secondary particles that can be detected by instruments on the ground. Most cosmic rays are relatively low energy, but a small fraction have incredibly high energies, sometimes exceeding 10 circumflex 20 electron volts, over 1,000,000 times more energetic than the particles produced in the Large Hadron Collider. The source of these ultra-high energy cosmic rays is unknown. They are so powerful that they should have been slowed down or deflected by interactions with the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe. This slowing effect is known as the Greisen-Zatsepin-Kuzmin (GZK) cutoff, which predicts that cosmic rays with energies above a certain threshold should be rare or non-existent because they lose energy over vast distances. Yet observations have found that these ultra-high energy cosmic rays do exist, and they seem to defy the GZK cutoff. This raises questions about where these cosmic rays come from and how they can travel such immense distances without losing their energy. Some scientists have proposed that these cosmic rays might be produced by exotic objects like supermassive black holes, rapidly rotating neutron stars, or even the decay of hypothetical particles from the early universe. Others suggest that they could be the result of interactions in regions of space where magnetic fields are extremely strong, allowing the particles to be accelerated to such high energies. Despite these theories, the mystery of ultra-high energy cosmic rays remains unsolved. Their detection is challenging, as they are incredibly rare, with only a few being detected each year. To study them, scientists use massive detectors spread over large areas, such as the Pierre Auger Observatory in Argentina, which covers over 3,000 square kilometers. Even with these efforts, the exact sources and mechanisms that produce these cosmic rays continue to elude us. Celestial oddities. In the vast expanse of space, where the familiar orbits of planets and the steady glow of stars provide a sense of order, there are occasional intrusions of the strange and unexplained. These celestial oddities capture our attention, not just for their rarity, but for the mysteries they bring with them, mysteries that challenge our understanding of the cosmos and provoke our imagination. Among these oddities, two have sparked particular intrigue: the enigmatic interstellar visitor named Oumuamua and the mysterious behavior of Tabbys Star. In October 2017, astronomers at the Haleakala Observatory in Hawaii spotted something unusual. It was a small, elongated object moving rapidly through the solar system, unlike anything they had seen before. Initially thought to be a comet or asteroid, further observations revealed that this object was unlike any known celestial body. Named Oumuamua, which means scout or messenger in Hawaiian, it was quickly recognized as the first interstellar object ever detected passing through our solar system. Oumuamua's trajectory indicated that it came from beyond our solar system, entering at an unusual angle and moving too fast to be bound by the Sun's gravity. This discovery alone made Oumuamua remarkable, but its physical characteristics made it even more puzzling. Unlike typical comets, Oumuamua showed no signs of a tail or coma, the cloud of gas and dust that usually forms when a comet approaches the Sun. It was also highly elongated, with a shape more like a cigar or a needle than the round or irregular shapes typically seen in asteroids. As astronomers studied Oumuamua, they found more anomalies. Its brightness varied dramatically, suggesting it was tumbling end over end as it moved through space. Additionally, as it passed by the Sun, it accelerated in a way that could not be fully explained by gravity alone. This led to speculation about what could be causing the acceleration. Was it due to outgassing, as would be expected from a comet, even though no gas or dust was detected? Or was something else at play? The unusual properties of Oumuamua led to a wide range of theories. Some scientists suggested that it might be a fragment of a larger object, perhaps broken off during a close encounter with a star. Others proposed that it could be a piece of a planetesimal, an early building block of a planet, ejected from its home system during the chaotic early stages of planetary formation. More speculative ideas even considered the possibility that Oumuamua might be an artificial object, perhaps a probe sent by an advanced civilization, its shape and behavior the result of an alien design. Despite extensive study, many questions about Oumuamua remain unanswered. Its brief passage through the solar system, less than a year from detection to its departure, meant that astronomers had limited time to observe it. By the time these mysteries were fully recognized, Oumuamua was already on its way out of the solar system, too far away to study in detail. It left behind a trail of questions. What was it? Where did it come from? And will we ever encounter something like it again? While Oumuamua provided a fleeting glimpse of an interstellar oddity, another celestial mystery has lingered much longer in the night sky. In 2015, astronomers studying data from the Kepler Space Telescope noticed something strange about a star located about 1,470 light-years from Earth in the constellation Cygnus. The star, officially known as KIC 8462852, but more commonly referred to as Tabbys Star, exhibited unusual dimming patterns that could not be easily explained by any known astrophysical phenomena. Most stars, when observed over time, show regular patterns of brightness. If a planet passes in front of a star, it causes a brief dip in brightness, a telltale sign of a transiting exoplanet. But Tabbys Star did not behave this way. Instead, its brightness dipped irregularly and unpredictably, sometimes by as much as 22%, far greater than the slight dimming caused by a planet. Moreover, these dimming events did not follow any regular pattern, making it difficult to explain them using conventional models of planetary orbits or stellar activity. The mystery of Tabbys Star quickly captured the imagination of both scientists and the public. Initial theories included the possibility of a swarm of comets passing in front of the star, creating the irregular dimming. Another idea was that a large cloud of dust or debris was orbiting the star, occasionally blocking its light. However, these explanations had their own challenges. For example, a cloud of debris dense enough to cause such significant dimming should have emitted infrared radiation, but no such excess infrared radiation was detected. The unusual behavior of Tabbys Star led to a more speculative hypothesis, one that has fascinated people for decades: the possibility of an alien megastructure. Some scientists and enthusiasts wondered if the irregular dimming could be caused by a massive structure, such as a Dyson sphere, a theoretical construct envisioned by physicist Freeman Dyson. A Dyson sphere would be a colossal structure built by an advanced civilization to capture energy from its star, and the dimming of Tabbys Star might be the result of such a structure partially blocking the star's light. While the idea of an alien megastructure made headlines and captured the public's imagination, most scientists remained cautious. The lack of additional evidence supporting the alien hypothesis, coupled with the likelihood of more mundane explanations, led many to focus on natural causes. Ongoing studies, including observations with the Green Bank telescope and other instruments, have aimed to detect any potential signals from the star that might indicate the presence of an advanced civilization, but so far, nothing conclusive has been found. Recent research has suggested that the dimming of Tabbys Star might be due to a combination of factors, including a large number of small opaque objects like dust or fragments of comets. However, the exact nature of these objects and their distribution remains uncertain. The star continues to be monitored, and as new data becomes available, scientists hope to unravel the mystery behind its unusual behavior. The stories of Oumuamua and Tabbys Star remind us that the universe is full of surprises, and that even with our advanced technology and knowledge, there are still many things we do not fully understand. These celestial oddities challenge our assumptions and push the boundaries of what we know, inviting us to explore the unknown and consider possibilities that lie beyond our current understanding. Galactic Mysteries. In the sprawling cosmos, where galaxies spin in elegant spirals and stars burst into life and death with dramatic flair, there are grand mysteries that challenge our understanding of the universe's very structure. Among these mysteries are the strange alignments of quasars, some of the brightest and most energetic objects in the universe, and the curious pattern found in the cosmic microwave background, CMB. The afterglow of the Big Bang, which has been dubbed the axis of evil. These phenomena raise questions about the nature of the universe on the largest scales, hinting at forces or structures that we have yet to fully comprehend. Quasars are among the most luminous and distant objects in the universe. Powered by supermassive black holes at the centers of young galaxies, these incredibly bright beacons emit more energy than entire galaxies and can be seen across vast stretches of space and time. For decades, quasars have been invaluable tools for astronomers, serving as lighthouses that help map the distant universe and probe its early history. But in recent years, an unexpected and puzzling phenomenon has come to light: the apparent alignment of the spin axes of quasars across billions of light years. In a universe where the orientation of galaxies and quasars should be random, with no preferred direction, the discovery of these alignments has been startling. When astronomers examined the polarization of light coming from these quasars, essentially the direction in which their light waves oscillate, they found that the spin axes of quasars in certain regions of the sky appeared to be aligned with each other. Even more intriguingly, these alignments seem to occur over incredibly vast distances, spanning billions of light years and encompassing regions of space that should be entirely unconnected. This discovery challenges the standard cosmological model, which assumes that on the largest scales, the universe is isotropic and homogeneous, meaning it should look the same in all directions and from all locations. The aligned quasars suggest that there might be large-scale structures or forces in the universe that we do not yet understand, something that could influence the orientation of objects over vast distances. One theory is that these alignments could be related to the large-scale structure of the universe itself, possibly linked to cosmic filaments, long, thread-like structures made up of galaxies and dark matter that connect clusters of galaxies together. If quasars are forming along these filaments, their alignment might be influenced by the structure of the cosmic web. However, the exact mechanism behind this remains unclear, and the alignments continue to be a topic of intense study and debate among astronomers. While the alignment of quasars challenges our understanding of the universe's structure, another cosmic puzzle lies even closer to the origin of everything: the cosmic microwave background, CMB. The CMB is the faint glow of radiation left over from the Big Bang, the oldest light in the universe, which has been traveling through space for nearly 14 billion years. It is a critical piece of evidence for the Big Bang theory and provides a snapshot of the universe when it was just 380,000 years old, a time when it was a hot, dense plasma. The CMB is remarkably uniform, with only tiny fluctuations in temperature that correspond to the seeds of the large-scale structures we see in the universe today. However, when scientists analyzed the CMB data in detail, they discovered something unexpected: a large-scale pattern in the temperature fluctuations that seemed to indicate a preferred direction in space. This pattern was first identified in 2005 and became known as the axis of evil. The axis of evil refers to an apparent alignment of temperature anomalies in the CMB that stretches across the sky, defying the expectation that the universe should have no preferred direction on such large scales. According to the standard model of cosmology, the universe should be isotropic, with no special directions or alignments. The discovery of this axis was surprising and controversial because it suggests that there might be something fundamentally wrong with our understanding of the early universe, or that there is a feature of the universe we have yet to account for. Several theories have been proposed to explain the axis of evil. One possibility is that it is simply a statistical fluke, a coincidence that appears significant but is actually random. However, the persistence of the pattern across multiple observations, including those from the Planck satellite, has led some scientists to consider other explanations. One idea is that the axis of evil could be the result of a previously unknown feature of the universe, such as a large-scale anisotropy, a difference in the distribution of matter or energy that could have influenced the CMB. Another possibility is that it could be linked to the shape of the universe itself. While most evidence suggests that the universe is flat, it is also possible that it has a slight curvature, or that it is shaped in a way that causes certain patterns to emerge on large scales. Some more speculative theories even suggest that the axis of evil could be a sign of new physics, perhaps related to the effects of dark energy, dark matter, or even multiple universes. If the universe is part of a larger multiverse, with different regions having different properties, the axis of evil might be a reflection of those other regions interacting with our own universe. Despite these efforts to explain the axis of evil, it remains one of the most intriguing and contentious anomalies in modern cosmology. Some scientists argue that more data and better understanding of cosmic phenomena might eventually resolve the issue, possibly revealing that the axis is less significant than it currently appears. Others believe that it might point to a deeper, more profound aspect of the universe that we are only beginning to uncover. The mysteries of the quasi-alignments and the axis of evil in the CMB highlight the complexity and vastness of the universe, reminding us that even with all our technological advancements and scientific theories, there is still much we do not understand. These phenomena challenge our assumptions about the universe's structure and origins, pushing us to reconsider what we know and to explore new ideas that might explain these cosmic oddities, the nature of time and space. In the endless expanse of the universe, where the forces of gravity and energy weave the cosmic fabric, there is perhaps no greater mystery than the nature of time and space themselves. These fundamental aspects of our reality, which seem so familiar in our daily lives, become deeply enigmatic when examined on the grandest scales or in the most extreme environments. The flow of time, especially near black holes, raises profound questions that challenge our understanding of the laws of physics. Meanwhile, in the cold depths of space, a peculiar feature in the cosmic microwave background known as the cold spot hints at mysterious forces at play in the structure of the universe. Time, as we experience it, flows in one direction, forward. We move from the past through the present and into the future in a seemingly irreversible process. This perception of time's arrow is closely tied to the second law of thermodynamics, which states that the total entropy, or disorder, of a closed system will always increase over time. This law explains why we remember the past but not the future, why broken eggs do not spontaneously reassemble, and why the universe evolves from states of lower entropy to higher entropy. However, when we venture into the realm of black holes, this straightforward picture of time begins to unravel. Black holes, with their immense gravitational pull, warp the fabric of space and time around them in ways that defy ordinary intuition. As matter approaches a black hole, time appears to slow down relative to an outside observer, a phenomenon predicted by Einstein's theory of general relativity. But the true strangeness of time in black holes lies deeper, in what is known as the Pauling paradox. The Pauling paradox arises from the apparent contradiction between the flow of time and the laws of thermodynamics in the context of black holes. According to the second law of thermodynamics, entropy should always increase, even within a black hole. But when a black hole swallows matter, the information about that matter, its exact state, position, and energy, seems to be lost forever behind the event horizon, the boundary beyond which nothing can escape. This loss of information would imply a decrease in entropy, seemingly violating the second law. To resolve this paradox, physicists have proposed that the information is not truly lost, but somehow encoded on the event horizon itself, possibly through quantum effects. This idea led to the development of the holographic principle, which suggests that all the information contained in a three-dimensional region of space can be described by information on a two-dimensional surface surrounding it. In the case of a black hole, this surface would be the event horizon, which might store the information about everything that has fallen into the black hole. Stephen Hawking famously suggested that black holes could emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation would carry away energy and information, leading to the gradual evaporation of the black hole over time. If this is the case, then the information about the matter that fell into the black hole would eventually be released back into the universe, preserving the second law of thermodynamics. However, this raises further questions about the nature of time and information in the universe, and whether our current understanding of these concepts is incomplete. The nature of time within black holes and the Pauling paradox remain areas of active research and debate among physicists. They force us to confront the limits of our knowledge and to explore the possibility that time and space might behave in ways we have yet to fully understand, especially under extreme conditions. While the Pauling paradox challenges our understanding of time, another cosmic mystery lies in the structure of space itself, as revealed by the cosmic microwave background, CMB. The CMB is the afterglow of the Big Bang, the oldest light in the universe, providing a snapshot of the cosmos when it was just 380,000 years old. This radiation is remarkably uniform, but it contains slight fluctuations in temperature that correspond to the seeds of galaxies and large-scale structures in the universe. One of the most puzzling features of the CMB is the cold spot, a region of space that appears significantly cooler than the surrounding areas. Discovered in 2004 through data from the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite, the cold spot spans about 1,500 million light-years and is located in the southern hemisphere of the sky. Its temperature is about 70 microkelvin colder than the average CMB temperature, which might seem small, but in the context of the CMB, it's a significant anomaly. The cold spot poses a challenge to the standard model of cosmology, which predicts that temperature fluctuations in the CMB should be random and evenly distributed. The existence of such a large, cold region suggests that there might be some additional factor influencing the distribution of matter and energy in the universe. One possible explanation for the cold spot is the Sachs-Wolf effect, a phenomenon where gravitational fields can influence the temperature of the CMB. As photons from the CMB travel through space, they pass through regions of varying gravitational strength. When photons enter a gravitational well, such as that caused by a massive galaxy cluster, they gain energy, becoming slightly hotter. Conversely, as they climb out of a gravitational well, they lose energy, resulting in a cooler temperature. In the case of the cold spot, some scientists propose that it could be the result of a massive supervoid, a region of space with significantly lower density than the surrounding areas, As CMB photons pass through this supervoid, they would experience less gravitational pull, leading to a decrease in temperature as observed in the cold spot. However, the existence of such a supervoid has yet to be conclusively proven, and even if it does exist, it might not fully account for the cold spot's size and depth. Other, more speculative explanations for the cold spot have also been proposed. Some researchers have suggested that it could be evidence of a collision between our universe and another bubble universe in a larger multiverse. In this scenario, the cold spot would be the result of a region where our universe's spacetime collided with that of another universe, creating a distinct imprint on the CMB. Despite these theories, the true cause of the cold spot remains unknown. It serves as a reminder that our understanding of the universe is still incomplete, and that there may be forces or phenomena at play on the largest scales that we have yet to uncover. The Flyby Anomaly. A flyby anomaly is an event where spacecraft experience unexpected changes in speed as they pass by Earth. Along with this, there is the triple solar system, which involves complex and unpredictable interactions within systems containing 3 stars. The Flyby Anomaly is one of those peculiar phenomena that has puzzled scientists since it was first observed. Spacecraft, when sent on missions to explore the solar system and beyond, often perform flybys of Earth or other planets to gain a gravitational boost, a technique known as a gravity assist. This maneuver uses the gravity of a planet to accelerate a spacecraft, allowing it to reach higher speeds without using additional fuel. The calculations for such maneuvers are based on well-understood principles of celestial mechanics, and they have been successfully employed in numerous missions. However, starting in the 1990s, scientists began to notice something strange. As some spacecraft performed flybys of Earth, their speeds changed in ways that could not be explained by the known forces at play. The most famous of these cases involved the Galileo spacecraft, which in 1990 gained an unexpected and unexplained increase in speed as it flew past Earth on its way to Jupiter. Similar anomalies were later observed during flybys by other spacecraft, including the Near-Shoemaker, Cassini, and Rosetta missions. These speed changes were small, typically on the order of a few millimeters per second, but they were significant enough to be noticeable and could not be accounted for by the standard models of gravitational forces. The flyby anomaly was puzzling because the equations governing gravity and motion, as laid out by Isaac Newton and later refined by Albert Einstein, are among the most precisely tested and reliable in all of physics. Yet here was a situation where the spacecraft appeared to be gaining or losing speed in a way that those equations could not predict. Several theories have been proposed to explain the flyby anomaly. Some scientists suggest that it could be due to unaccounted for effects in the Earth's gravity field or in the distribution of mass within the planet. Others have speculated that it might be related to the spacecraft's interaction with the Earth's atmosphere, though the spacecraft were at altitudes where atmospheric drag should have been negligible. More exotic theories even consider the possibility of new physics, such as variations in the gravitational constant or the influence of dark matter. Despite these efforts, no definitive explanation for the flyby anomaly has been found. The phenomenon remains one of the more curious, unsolved mysteries in space exploration, a small but persistent reminder that even in the realm of precise science, unexpected surprises can occur. While the flyby anomaly challenges our understanding of spacecraft dynamics, another complex and perplexing problem arises in the context of multiple star systems, particularly those involving 3 stars. Known as the triple solar system problem, this issue involves predicting the motion of 3 stars that are gravitationally bound to each other. Unlike the relatively straightforward 2-body problem, where the orbits of 2 objects around their common center of mass can be precisely calculated, the 3-body problem introduces a level of complexity that makes exact predictions nearly impossible. In a triple star system, the gravitational forces between the stars create a constantly changing and highly sensitive environment. Even small differences in the initial conditions, such as the positions, velocities, or masses of the stars, can lead to drastically different outcomes over time. This sensitivity to initial conditions is a hallmark of chaotic systems, where small changes can lead to large, unpredictable variations in behavior. In such systems, long-term predictions become extremely difficult, if not impossible. One of the classic examples of a triple star system is Alpha Centauri, the closest star system to Earth, which consists of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B form a relatively close binary pair, while Proxima Centauri, a red dwarf, orbits them at a much greater distance. The dynamics of this system are complex, with the gravitational interactions between the 3 stars creating a constantly shifting balance that can lead to unpredictable orbital changes over long periods. The triple solar system problem has fascinated astronomers and mathematicians for centuries, ever since the problem was first formulated in the context of celestial mechanics. In the 18th century, mathematicians like Joseph-Louis Lagrange and Pierre-Simon Laplace made significant advances in understanding the motion of 3 bodies, but they also recognized the inherent difficulty in finding exact solutions. The problem is so complex that even with modern computers, it remains challenging to predict the long-term behavior of such systems with high accuracy. In many cases, the orbits in triple star systems are stable for long periods, with the stars following complex but regular paths around each other. However, in some situations, the system can become unstable, leading to dramatic events, such as one star being ejected from the system entirely, leaving the remaining stars to form a more stable binary pair. These ejections are a result of the chaotic nature of the 3-body interactions, where small perturbations can lead to significant changes in the system's dynamics. One of the reasons the triple solar system problem is so intriguing is that it touches on fundamental questions about the nature of chaos and order in the universe. While the motions of 2 bodies can be described with elegant, predictable equations, the introduction of a 3rd body creates a system where predictability gives way to complexity and chaos. This complexity is not just a mathematical curiosity. It has real implications for our understanding of the universe. For instance, the stability of planetary systems around triple star systems could be influenced by the chaotic interactions between the stars, affecting the potential habitability of planets in such systems. Despite the challenges, scientists have made progress in understanding triple star systems through a combination of numerical simulations and observational data. By studying known triple systems and simulating their dynamics, astronomers have begun to map out the conditions under which these systems remain stable or become chaotic. These studies provide valuable insights into the formation and evolution of star systems, as well as the role that chaos plays in shaping the universe. The Flyby Anomaly and the triple solar system problem highlight the complexity and unpredictability that can arise in the study of the cosmos. Both phenomena challenge our understanding of the laws of physics, revealing the limitations of our current models and the need for continued exploration and investigation. Whether it is the mysterious changes in spacecraft speeds during Earth flybys or the intricate dance of stars in a triple system, these puzzles remind us that the universe is a place of endless surprises, where even the most familiar forces can behave in unexpected ways. The search for missing pieces. The universe, in all its vastness and complexity, is a treasure trove of elements that make up everything we see, from the stars in the night sky to the atoms in our own bodies. These elements were forged in the hearts of stars and in the fiery aftermath of the Big Bang. Yet despite our detailed understanding of nuclear physics and the processes that created the elements, there are still puzzles that remain unsolved. One of the most intriguing of these is known as the lithium problem, a discrepancy between the predicted and observed amounts of lithium in the universe. This mystery, along with other unexplained chemical phenomena, challenges our understanding of the early universe and the processes that shaped its elemental makeup. In the moments following the Big Bang, the universe was a hot, dense soup of particles, protons, neutrons, electrons, and photons undergoing rapid changes. As the universe expanded and cooled, these particles began to combine to form the simplest elements. This process, known as Big Bang nucleosynthesis, occurred within the first few minutes after the Big Bang and resulted in the formation of hydrogen, helium, and small amounts of lithium and beryllium. These light elements became the building blocks for all the heavier elements that would be formed later in stars. The predictions of Big Bang nucleosynthesis are remarkably successful in explaining the observed abundances of hydrogen and helium in the universe. However, when it comes to lithium, specifically the isotope lithium-7, there is a significant discrepancy. According to the theoretical models, the amount of lithium-7 produced during the Big Bang should be about 3 times higher than what we actually observe in old stars, which serve as cosmic time capsules, preserving the elemental composition from the early universe. This difference between the predicted and observed lithium abundance is known as the lithium problem, and it has puzzled astronomers and cosmologists for decades. The lithium problem is not just a minor detail. It raises fundamental questions about our understanding of the early universe and the processes that governed it. If the predictions of Big Bang nucleosynthesis are so accurate for hydrogen and helium, why do they fail for lithium? This inconsistency suggests that there might be something missing in our models, or that some other processes might be at play that we have yet to fully understand. Several possible explanations for the lithium problem have been proposed, but none have provided a definitive answer. One possibility is that the models of Big Bang nucleosynthesis might need revision. Perhaps there are factors in the early universe, such as variations in the density of matter or the presence of additional particles, that we have not accounted for, which could alter the amount of lithium produced. Another idea is that lithium-7 might be destroyed in stars after it forms. Stars, especially older low-mass stars, can deplete lithium through nuclear reactions that occur in their interiors. This could mean that the lithium-7 present in these stars today is not representative of the original amount produced during the Big Bang, as some of it may have been destroyed over time. However, this explanation has its limitations, as it would require a very efficient mechanism for lithium destruction, one that current models struggle to fully explain. There is also the possibility that some unknown astrophysical processes could be responsible for the discrepancy. For instance, interactions between cosmic rays and interstellar matter, or other exotic processes involving dark matter or other unknown particles, could potentially affect the abundance of lithium. However, these ideas are speculative, and there is currently no direct evidence to support them. The lithium problem is not the only chemical mystery that challenges our understanding of the universe. There are other anomalies in the abundances of elements that suggest our models of stellar evolution and nucleosynthesis might be incomplete. For example, the observed abundances of certain isotopes in old stars, such as carbon-12 and oxygen-16, do not always match the predictions from models of stellar interiors and supernova explosions. These discrepancies hint at possible gaps in our knowledge of the processes that govern element formation and distribution in the universe. One such mystery involves the isotope ratios of certain elements, such as magnesium and silicon, in different regions of the galaxy. These ratios can provide clues about the history of star formation and the mixing of stellar material in the interstellar medium. However, in some cases, the observed ratios do not fit with the expected patterns based on current models. This suggests that there may be additional factors influencing the chemical evolution of galaxies, perhaps related to the dynamics of star formation, the effects of magnetic fields, or the role of cosmic rays. Another unexplained phenomenon is the apparent overabundance of certain heavy elements, such as europium and gadolinium, in some old stars. These elements are typically produced in supernova explosions and the merging of neutron stars, events that are relatively rare. The presence of these elements in large amounts in certain stars suggests that the history of star formation and element production in the universe might be more complex than we currently understand. It raises questions about the frequency and distribution of these rare astrophysical events, and how they contribute to the chemical enrichment of the galaxy. The study of cosmic chemical mysteries, like the lithium problem and other elemental anomalies, is crucial for our understanding of the universe's history and the processes that shaped it. These puzzles challenge us to look deeper into the mechanisms of nucleosynthesis, the life cycles of stars, and the interactions between matter and energy in space. Each of these mysteries represents a piece of a larger puzzle, one that could lead to new insights into the nature of the cosmos and the forces that govern it. As scientists continue to investigate these chemical anomalies, they use a variety of tools, from advanced telescopes that can observe the light spectra of distant stars to complex computer models that simulate the conditions of the early universe and the interiors of stars. These efforts aim to refine our understanding of the processes that created the elements and distributed them throughout the cosmos. The resolution of these mysteries may also have implications for other areas of physics, potentially leading to new discoveries in particle physics, cosmology, and astrophysics. The search for missing pieces in the cosmic chemical puzzle is a testament to the enduring curiosity and determination of scientists to understand the universe in all its complexity. It is a reminder that even in a field as well established as nuclear physics and cosmology, there are still unanswered questions and unexpected phenomena waiting to be explored. Each discovery, whether it solves a mystery or uncovers a new one, brings us closer to a more complete picture of the universe's origins and evolution. Unseen structures. As we delve deeper into the cosmos, we occasionally encounter anomalies that challenge our most fundamental assumptions about the universe. Among these is the axis of evil, a term used to describe a mysterious alignment observed in the cosmic microwave background, CMB, that seems to defy the expectation of a universe that should be isotropic, appearing the same in every direction. This anomaly, discovered in the data from the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite, has profound implications for our understanding of the universe's large-scale structure and the underlying principles that govern it. The CMB is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. It is one of the most critical pieces of evidence supporting the Big Bang theory, and its study has allowed cosmologists to refine their models of the early universe with remarkable precision. The CMB is mostly uniform, but it contains slight temperature fluctuations that represent the seeds of all future structures: galaxies, stars, and planets. These fluctuations are thought to be random, with no preferred direction or alignment, reflecting the isotropic nature of the universe. However, the axis of evil presents a significant challenge to this view. It refers to an unexpected alignment of temperature fluctuations in the CMB that seems to point in a particular direction across the sky. This alignment is at odds with the cosmological principle, which holds that the universe should be homogeneous and isotropic on large scales. The very existence of such a directional preference suggests that there may be something about the universe's large-scale structure that we do not yet understand. The implications of the axis of evil are far-reaching. If this alignment is not just a statistical fluke, but a real feature of the universe, it could force a re-evaluation of the standard model of cosmology. Some scientists have suggested that the axis of evil might indicate the presence of large-scale structures or fields that are not accounted for in current models. These could include exotic phenomena, like cosmic strings, remnants of phase transitions in the early universe, or large-scale anisotropies in the distribution of matter and energy. Another possibility is that the axis of evil could be a sign of new physics, pointing to a deeper layer of reality that our current theories do not capture. For instance, it might be related to the effects of dark energy, the mysterious force driving the accelerated expansion of the universe. Some theories suggest that dark energy could have spatial variations, creating regions with slightly different properties that could lead to the observed alignment. Alternatively, the axis of evil might be evidence of a more fundamental symmetry breaking in the early universe, leading to anisotropies that persist to this day. The challenge posed by the axis of evil extends beyond theoretical considerations. It also raises questions about the accuracy and interpretation of the data used to detect it. Some skeptics argue that the anomaly might be the result of systematic errors in the measurements or biases introduced by the way the data is processed. For example, the complex procedures required to separate the CMB signal from foreground emissions, such as those from the Milky Way, could introduce artifacts that mimic a real alignment. Despite these uncertainties, the axis of evil remains one of the most intriguing and controversial topics in cosmology. It serves as a reminder that our understanding of the universe is still evolving, and that even the most well-established theories can be challenged by new observations. As future missions continue to study the CMB with greater precision, the hope is that we will either confirm the reality of the axis of evil or find explanations that reconcile it with the standard model. Whatever the outcome, the investigation of this anomaly is likely to yield valuable insights into the nature of the universe and the forces that shape it. While the axis of evil challenges our understanding of the universe's large-scale structure, another mystery, the Pioneer Anomaly, has raised questions about our knowledge of gravitational forces in the solar system. The Pioneer Anomaly refers to the unexpected deviations in the trajectories of the Pioneer 10 and Pioneer 11 spacecraft as they traveled through the outer solar system. Launched in the early 1970s, these spacecraft were the first to venture beyond the asteroid belt, providing humanity with its first close-up images of Jupiter and Saturn. The Pioneer Anomaly was first reported in the late 1980s, and for years it remained one of the most puzzling mysteries in space exploration. Various explanations were proposed, ranging from mundane possibilities, like the uneven emission of heat from the spacecraft's power sources, to more exotic ideas involving new physics. For instance, some researchers speculated that the anomaly could be evidence of a deviation from Newton's law of gravity at large distances, perhaps indicating the influence of dark matter or the effects of a hypothetical fifth force. The search for the cause of the Pioneer Anomaly involved a detailed reanalysis of the spacecraft's trajectories, taking into account every possible factor that could influence their motion. This included the gravitational effects of the planets and the Sun, the pressure of sunlight and the solar wind, and even the thermal recoil force, the tiny push exerted by the infrared radiation emitted by the spacecraft's power systems. In 2012, a comprehensive study by a team of researchers concluded that the Pioneer Anomaly could be fully explained by thermal recoil force. As the spacecraft's power sources generated heat, some of that heat was radiated asymmetrically, creating a small but constant force that gradually slowed the spacecraft. This explanation, while mundane, was a significant achievement in precision engineering and demonstrated the importance of accounting for even the smallest effects in deep space navigation. However, the resolution of the Pioneer Anomaly did not entirely close the door on the mystery. Some researchers continue to investigate whether other, more subtle effects might be at play, or whether the anomaly could have implications for our understanding of gravity and space-time. The case of the Pioneer Anomaly highlights the delicate balance between known physics and the potential for new discoveries. It also underscores the need for continued vigilance in the study of space missions, where even the smallest discrepancies can lead to profound insights. The axis of evil and the Pioneer Anomaly, each in their own way, challenge our understanding of the universe and the forces that govern it. These anomalies push the boundaries of our knowledge, forcing us to question assumptions and explore new possibilities. They remind us that the universe is not always as predictable as our theories might suggest, and that even well-established models can be confronted with unexpected data. The future of black hole research. As we continue to probe the depths of the cosmos, Few phenomena capture our imagination and challenge our understanding of the universe more than black holes. These enigmatic objects, with gravitational pulls so strong that not even light can escape, represent some of the most extreme environments in the universe. Black holes push the boundaries of our knowledge of physics, especially in the realms of quantum mechanics and general relativity. As we look to the future of black hole research, two key areas stand out: the resolution of the information paradox and the profound role that black holes play in the evolution of galaxies. The information paradox is one of the most intriguing and hotly debated topics in modern theoretical physics. At its heart lies a fundamental question: what happens to the information about the physical state of matter when it falls into a black hole? According to the laws of quantum mechanics, information about the physical state of a system should never be destroyed. This principle, known as unitarity, implies that the past and future states of a quantum system are always connected, and information is preserved even if the system evolves in complex ways. However, black holes seem to defy this principle. When matter falls into a black hole, it is thought to be crushed to a singularity, a point of infinite density where the known laws of physics break down. The event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull, appears to trap everything, including information, making it inaccessible to the outside universe. This leads to the troubling possibility that information about the matter that falls into a black hole is lost forever, violating the principles of quantum mechanics. This apparent contradiction between quantum mechanics and general relativity was first highlighted by Stephen Hawking in the 1970s. Hawking proposed that black holes could emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Over time, this radiation would cause the black hole to lose mass and eventually evaporate completely. But if the black hole evaporates, what happens to the information it contains? Hawking initially suggested that this information could be lost forever, leading to the information paradox. The idea that information could be lost in black holes sparked intense debate and led to a significant conflict between quantum mechanics and general relativity. If information is indeed lost, it would imply that quantum mechanics is not a complete theory, which would have profound implications for our understanding of the fundamental laws of physics. Over the years, various solutions to the information paradox have been proposed, but none have been universally accepted. Some physicists argue that the information might be encoded in the Hawking radiation itself, though this idea raises questions about how such information could be retrieved from a seemingly random and thermal radiation. Others suggest that the information might be stored on the event horizon, in a way that is preserved even as the black hole evaporates. This concept led to the development of the holographic principle, which posits that all the information contained within a volume of space can be represented on the surface surrounding that volume. In recent years, the concept of firewalls has been introduced as a potential resolution to the paradox. According to this idea, the event horizon of a black hole might not be a smooth, benign boundary, but rather a highly energetic region where the laws of physics undergo dramatic changes. In this scenario, as matter approaches the event horizon, it could be incinerated by the firewall, releasing its information in a form that is somehow preserved and encoded in the Hawking radiation. Despite these theories, the information paradox remains unresolved, and it continues to be a central focus of research in theoretical physics. Resolving the paradox will likely require a deeper understanding of quantum gravity, a theory that successfully combines the principles of quantum mechanics with general relativity. This pursuit is at the cutting edge of modern physics, where black holes serve as a unique testing ground for new ideas about the nature of reality. While the information paradox represents the theoretical challenges posed by black holes, these objects also play a critical and practical role in the evolution of galaxies. Black holes, particularly supermassive black holes that reside at the centers of most galaxies, have a profound influence on the formation and growth of galaxies. Understanding this role is crucial for unraveling the history and future of the cosmos. Supermassive black holes, with masses ranging from millions to billions of times that of our Sun, are thought to have formed early in the history of the universe, possibly as a result of the collapse of massive gas clouds or from the merging of smaller black holes. These giant black holes are found at the centers of most large galaxies, including our own Milky Way, where the supermassive black hole known as Sagittarius A** resides. The relationship between supermassive black holes and their host galaxies is one of the most significant areas of study in modern astrophysics. Observations have revealed a strong correlation between the mass of a galaxy's central black hole and the properties of the galaxy's bulge, such as its mass and velocity dispersion. This correlation, known as the M-sigma relation, suggests that the growth of black holes and galaxies are closely linked. One way in which supermassive black holes influence their host galaxies is through a process known as feedback. As matter falls into a black hole, it forms an accretion disk and releases enormous amounts of energy in the form of radiation and powerful jets. This energy can heat the surrounding gas, preventing it from cooling and collapsing to form new stars. In some cases, the jets from a black hole can drive material out of the galaxy entirely, slowing down or even halting star formation. This feedback mechanism is thought to play a crucial role in regulating the growth of galaxies and in determining their structure and evolution. Despite these insights, many questions remain about the role of black holes in galactic evolution. For instance, how do supermassive black holes form in the first place? While there are several theories, ranging from the direct collapse of massive gas clouds to the merging of smaller black holes, the exact mechanisms are still uncertain. Additionally, the process by which black holes and galaxies co-evolve is not fully understood. How do galaxies feed their central black holes? And how does this feeding influence the overall dynamics of the galaxy? These are questions that astronomers are actively investigating using a combination of observations, simulations, and theoretical models. Another area of active research involves the study of intermediate mass black holes, which are thought to exist between the stellar mass black holes formed from the collapse of massive stars and the supermassive black holes at the centers of galaxies. These intermediate mass black holes could provide key insights into the formation and growth of supermassive black holes, but their existence and properties are still not well established. The study of black holes is also intimately connected with the search for gravitational waves, ripples in spacetime, caused by the acceleration of massive objects. The detection of gravitational waves from merging black holes by the LIGO and Virgo observatories has opened up a new way to study these mysterious objects, allowing us to observe the dynamics of black hole mergers and to probe the properties of spacetime in extreme conditions. The mysteries surrounding black holes, from the information paradox to their role in galactic evolution, remind us that the universe is a place of profound complexity and wonder. As we continue to explore these enigmas, we are not just seeking to understand black holes themselves, but also to unlock the deeper principles that govern the cosmos. The answers we find may lead to new discoveries that reshape our understanding of the universe, or they may open up new questions that push the boundaries of human knowledge even further. Solar System Mysteries. Our solar system, though relatively small compared to the vast expanse of the universe, still holds many mysteries that continue to intrigue and puzzle scientists. Among these are the enigmatic Planet 9, a hypothesized giant planet that might lurk in the distant reaches of our solar system, and the curious case of Saturn's rings, which, despite being one of the most iconic features in our celestial neighborhood, still confound scientists with questions about their origins and age. These mysteries remind us that, even close to home, there are still many unknowns waiting to be uncovered. In recent years, the idea of a ninth planet, far beyond the orbit of Neptune, has captivated the scientific community and the public alike. This hypothetical world, known as Planet 9, was proposed to explain the peculiar orbits of certain distant objects in the solar system, specifically those in the Kuiper Belt, a vast region of icy bodies that extends beyond Neptune. Some of these objects, known as trans-Neptunian objects, TNOs, exhibit highly elongated and tilted orbits that cannot be easily explained by the gravitational influence of the known planets. The concept of Planet 9 was first introduced in 2016 by astronomers Konstantin Batygin and Mike Brown, who noticed that several TNOs had orbits that were strangely clustered together in a way that suggested they were being shepherded by a massive, unseen planet. According to their calculations, Planet 9 would need to be at least 10 times the mass of Earth and orbit the Sun at a distance between 300 and 1,000 astronomical units, AU, far beyond the orbit of Pluto, which lies at an average distance of about 40 AU from the Sun. The existence of Planet 9 would help explain not only the odd orbits of these TNOs, but also other anomalies in the outer solar system. For instance, some distant objects have orbits that are perpendicular to the plane of the solar system, a feature that could be explained by the gravitational influence of a massive distant planet. Additionally, Planet 9 could account for the mysterious alignment of the orbits of these distant objects, which seem to be pointing in roughly the same direction, as if guided by a single, unseen force. Despite the compelling evidence, Planet 9 has yet to be directly observed. This is not entirely surprising, given its presumed distance, and the fact that it would be relatively faint compared to the known planets. Detecting such a distant object would require highly sensitive instruments and a careful search of the sky, which is ongoing. Several large-scale surveys, including those conducted by the Subaru telescope in Hawaii, are actively searching for Planet 9, but so far it remains elusive. The search for Planet 9 is a challenging endeavor, not only because of its faintness, but also because of the vast area of the sky that needs to be covered. The planet's potential orbit could take thousands of years to complete, meaning that it could be anywhere along its path, making the task of finding it akin to searching for a needle in a cosmic haystack. Nonetheless, astronomers are optimistic that with continued observations, and perhaps the use of next-generation telescopes, Planet 9 may eventually be found. If Planet 9 is confirmed, it would represent a significant addition to our understanding of the solar system. It would not only fill a major gap in our knowledge of the solar system's structure, but also offer new insights into the formation and evolution of planetary systems in general. The discovery would raise new questions about how such a massive planet ended up in such a distant orbit. Was it formed in situ, or was it ejected from the inner solar system by gravitational interactions with the other giant planets? These are questions that scientists would eagerly seek to answer if Planet 9 is found. While the mystery of Planet 9 lies at the edge of the solar system, another enduring enigma can be found much closer to the Sun, in the majestic rings of Saturn. Saturn's rings are one of the most recognizable features in the solar system, a stunning halo of icy particles that encircles the gas giant in a broad, flat disk. Despite being one of the most studied planetary features, the origins and age of Saturn's rings remain a topic of intense debate and investigation. Saturn's rings are composed primarily of water ice, with some dust and rocky material mixed in. They are divided into several distinct rings, labeled A through F, with the main rings A, B, and C being the most prominent. These rings are incredibly thin, only a few tens of meters thick, but they span over 200,000 kilometers in diameter, making them visible even from Earth with small telescopes. One of the most intriguing aspects of Saturn's rings is their brightness. The rings are exceptionally reflective, suggesting that they are composed of relatively clean ice, which in turn implies that they might be much younger than the planet itself. If the rings were billions of years old as Saturn itself, they would likely have accumulated a significant amount of dust and debris, making them darker and less reflective. However, their pristine appearance suggests they could be only a few 100 million years old, perhaps a mere fraction of the age of the solar system. This leads to the question of how Saturn's rings formed and why they are so young in appearance. Several theories have been proposed to explain the origin of the rings. One possibility is that they are the remnants of a moon or a comet that was torn apart by Saturn's powerful gravity. If a moon or comet ventured too close to the planet, the tidal forces could have ripped it apart, scattering its icy debris into a ring around Saturn. Over time, this material could have coalesced into the rings we see today. Another theory suggests that the rings could have formed from material left over from the formation of Saturn itself. In this scenario, the rings would be much older, perhaps dating back to the early days of the solar system. However, if the rings are indeed ancient, their brightness and purity would need to be explained by some process that continually cleans and refreshes the ice, keeping it free of dust and other contaminants. One such process could involve the collision of icy particles within the rings, which would grind them down and expose fresh ice surfaces, maintaining their reflective quality. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided a wealth of data that has helped to refine our understanding of the rings. Cassini's observations revealed intricate details about the structure and composition of the rings, including the presence of tiny moons embedded within the rings, and the discovery of propeller-like features caused by the gravitational influence of these moons. Cassini also found evidence that the rings are losing material at a faster rate than previously thought, as particles from the rings are being pulled into Saturn by its gravity in a process known as ring rain. This finding suggests that the rings might be more transient than once believed, possibly dissipating over the next few 100 million years. Despite these insights, many questions about Saturn's rings remain unanswered. The precise age of the rings is still a matter of debate, as is the exact mechanism by which they formed. The rings' dynamic nature, with ongoing processes that shape and reshape their structure, adds another layer of complexity to the puzzle. Understanding Saturn's rings is not only important for unraveling the history of the planet itself, but also for providing clues about the formation and evolution of other planetary ring systems, both within our solar system and beyond. The mysteries of Planet 9 and Saturn's rings highlight the fact that, even in our own solar system, there are still many unanswered questions and unexplored frontiers. These mysteries drive scientists to continue exploring and questioning, using the latest technology and techniques to probe deeper into the unknown. As we search for Planet 9 and study the rings of Saturn, we are not just learning about these specific phenomena, we are also expanding our knowledge of the solar system as a whole, gaining new insights into the processes that have shaped it over billions of years. Unusual objects. In the vast expanse of the universe, where the laws of physics govern the birth, life, and death of celestial objects, there are phenomena that defy our expectations and challenge our understanding. Among these are the mysterious zombie stars, which appear to have defied the finality of death, continuing to shine after experiencing what should have been their catastrophic end. Equally intriguing are rogue planets, lonely worlds that wander the galaxy unbound by the gravitational pull of a star. These unusual objects offer glimpses into the strange and often surprising behaviors of the cosmos. Zombie stars are a phenomenon that has puzzled astronomers and astrophysicists. In the life cycle of a typical star, the final act is often a supernova, a powerful explosion that marks the end of the star's life, leaving behind either a neutron star, black hole, or in some cases, nothing at all. However, some stars appear to have survived this cataclysmic event, continuing to shine even after they should have been destroyed. These stars, often referred to as zombie stars, challenge our understanding of stellar death and the processes that lead to a supernova. The concept of a zombie star arises from observations of certain supernovae that do not conform to the expected patterns. In a typical Type Ia supernova, a white dwarf, a small, dense remnant of a star that has exhausted its nuclear fuel, accumulates material from a companion star until it reaches a critical mass. At this point, the white dwarf undergoes a runaway thermonuclear reaction, leading to a violent explosion that obliterates the star. The explosion is so intense that it typically leaves nothing behind. However, astronomers have observed instances where a supernova explosion occurs, yet a remnant star remains visible, continuing to shine long after the explosion. One such example is a supernova known as SN 2009 IP, which was first detected in 2009 in a galaxy about 80 million light-years from Earth. This supernova exhibited unusual behavior, with multiple outbursts over several years before eventually fading. But instead of disappearing, as expected, a faint object remained visible at the location of the explosion, suggesting that the progenitor star had somehow survived. These zombie stars may be the result of a unique type of supernova known as a partial supernova or failed supernova. In this scenario, the explosion is not powerful enough to completely destroy the star. Instead, the outer layers of the star are ejected, but the core remains intact. This remnant core may continue to shine, albeit in a diminished state, effectively becoming a zombie star. The exact mechanisms behind such partial supernova are still not fully understood, but they could involve complex interactions between the star's core and its outer layers, or the presence of a binary companion that influences the dynamics of the explosion. Another intriguing possibility is that some zombie stars are the result of a merger between two white dwarfs. In this scenario, the combined mass of the white dwarfs might trigger a supernova-like event, but instead of completely destroying the merged object, it might leave behind a new, more massive white dwarf that continues to emit light. This would create the appearance of a star that has returned from the dead, defying the normal expectations of stellar evolution. Zombie stars raise important questions about the end stages of stellar evolution and the conditions under which stars explode as supernovae. They also challenge the assumptions that astronomers have traditionally made about the fates of stars and the nature of supernova explosions. As more zombie stars are discovered and studied, they may provide new insights into the complex and varied ways that stars can end their lives, revealing the universe to be even more dynamic and unpredictable than previously thought. While zombie stars hint at the strange ways in which stars can survive death, rogue planets tell a different kind of cosmic tale, one of isolation and survival in the cold, dark reaches of interstellar space. Unlike the planets in our solar system, which are bound by gravity to orbit the Sun, rogue planets have no such tether. They drift through the galaxy alone, unanchored to any star, wandering through the void with only the faint light of distant stars to guide them. The existence of rogue planets was long theorized, but only confirmed in recent years. These planets, sometimes called free-floating planets, are thought to be as common as stars, yet they remain difficult to detect because they emit very little light. Without a parent star to illuminate them, rogue planets are essentially invisible against the backdrop of space, detectable only through indirect methods such as gravitational microlensing, where the planet's gravity bends and magnifies the light of a distant star as it passes in front of it. The formation of rogue planets is a subject of ongoing research and debate. One possible explanation is that these planets formed in the same way as regular planets, within the protoplanetary disks of gas and dust that surround young stars. However, during the chaotic early stages of a solar system's formation, gravitational interactions between planets or between planets and passing stars could have ejected some planets from their orbits, sending them careening into interstellar space. Another possibility is that rogue planets formed directly from the collapse of gas clouds, similar to the process that forms stars but on a much smaller scale. If a gas cloud is not massive enough to ignite nuclear fusion at its core, it might instead form a planet-sized object that remains isolated from any star. These isolated planets would then drift through the galaxy as rogue planets, never having been part of a star system. The discovery of rogue planets has significant implications for our understanding of planetary formation and the distribution of planets in the galaxy. If rogue planets are as common as some studies suggest, it would mean that planets can form and survive in a much wider range of environments than previously thought. It also raises the possibility that there could be many more planets in the galaxy than there are stars, with countless worlds hidden in the darkness between the stars. The survival of rogue planets in the harsh conditions of interstellar space is another fascinating aspect of these objects. Without the warmth of a star, rogue planets would be extremely cold, with surface temperatures potentially close to absolute zero. However, it is possible that some rogue planets could retain internal heat from their formation or from radioactive decay, providing a faint glimmer of warmth that might allow subsurface oceans or atmospheres to persist for billions of years. This has led to speculation about the potential for life on rogue planets, although the extreme conditions would make any such life very different from what we know on Earth. The study of rogue planets is still in its early stages, but advances in observational techniques and the development of new telescopes are likely to lead to more discoveries in the coming years. As more rogue planets are found, scientists hope to learn more about their origins, their physical properties, and their potential for hosting life. These lonely wanderers of the galaxy represent a new frontier in planetary science, offering insights into the diversity of worlds that exist in our universe and challenging our understanding of what it means to be a planet. Zombie stars and rogue planets, each in their own way, defy the expectations we have for celestial objects. They remind us that the universe is full of surprises, where even the most well-established processes, like the death of a star or the formation of a planet, can take unexpected turns. These unusual objects not only deepen our appreciation for the complexity of the cosmos, but also push the boundaries of our knowledge, encouraging us to continue exploring and questioning the nature of the universe. Unexplained cosmic patterns. While our understanding of the cosmos has grown immensely over the past century, there remain cosmic patterns and structures that challenge our expectations and defy easy explanation. Among these are the large quasar groups, LQGs, colossal assemblies of quasars that seem to violate the expected uniformity and scale of the universe, and the mysterious imprints left by baryon acoustic oscillations, BAOs, ancient sound waves from the early universe that have shaped the distribution of galaxies in ways we are still trying to fully understand. Quasars are some of the brightest and most energetic objects in the universe, powered by supermassive black holes at the centers of young galaxies. These distant beacons emit tremendous amounts of light, outshining entire galaxies and allowing us to see them across vast cosmic distances. Quasars are often used as markers to study the large-scale structure of the universe because their extreme brightness makes them visible even at great distances. In the 1980s, astronomers began to notice something unusual when they mapped the distribution of quasars across the sky. Instead of being randomly scattered, as one might expect in a uniformly expanding universe, some quasars appeared to be grouped together in enormous structures that span billions of light-years. These structures, known as large quasar groups, LQGs, challenge the prevailing cosmological principle, which posits that the universe is homogeneous and isotropic on the largest scales, meaning it should look roughly the same in every direction, with no preferred locations or alignments. One of the most famous LQGs is the huge LQG, discovered in 2012, which stretches across 4 billion light-years and contains 73 quasars. To put this in perspective, the size of this structure is more than 1,600 times the distance from the Milky Way to the Andromeda Galaxy, and it is far larger than the scale at which we would expect to see any coherent structure in the universe. According to the standard cosmological model, structures larger than about 1.2 billion light-years should not exist because the universe has not had enough time since the Big Bang for such large structures to form through gravitational interactions. The existence of LQGs raises profound questions about our understanding of the universe's large-scale structure. Are these structures a sign that our models of the universe's formation and evolution are incomplete? Or could they be the result of statistical anomalies, rare but possible fluctuations in the distribution of matter and energy? Some scientists have suggested that LQGs might be aligned along filaments of the cosmic web, the vast network of galaxies and dark matter that permeates the universe. These filaments could act as gravitational highways, guiding the formation of quasars and galaxies along specific directions, leading to the appearance of these large-scale structures. However, the sheer size of LQGs still poses a challenge to this explanation, as even the most generous models of cosmic structure formation struggle to account for structures on this scale. Some researchers have proposed that LQGs might be connected to primordial density fluctuations in the early universe, regions where the density of matter was slightly higher than average, leading to the formation of large clusters of galaxies and quasars. If these fluctuations were larger or more pronounced than current models suggest, they could potentially explain the existence of LQGs. Another possibility is that LQGs could be the result of unknown or poorly understood physical processes, such as interactions between dark matter and dark energy, or the effects of exotic particles that influence the formation of structures in the early universe. These ideas are still speculative, and much more research is needed to determine whether they can account for the observed patterns of quasars. The discovery of LQGs has sparked a renewed interest in studying the large-scale structure of the universe, with astronomers using increasingly sophisticated tools and techniques to map the distribution of quasars, galaxies, and dark matter. As we continue to refine our models and gather more data, we may eventually uncover the true nature of these colossal structures and their place in the cosmic landscape. While LQGs represent a challenge to our understanding of the universe's large-scale structure, another cosmic pattern, the baryon acoustic oscillations, BAOs, offers a window into the earliest moments of the universe and the processes that shape the distribution of galaxies. BAOs are the remnants of sound waves that propagated through the hot, dense plasma of the early universe shortly after the Big Bang. These sound waves, or pressure waves, were driven by the interplay between gravity, which pulled matter together, and radiation pressure, which pushed it apart. As the universe expanded and cooled, these sound waves left an imprint on the distribution of matter, creating regions of slightly higher and lower density. When the universe was about 380,000 years old, it cooled enough for protons and electrons to combine and form neutral hydrogen, allowing photons to travel freely through space, an event known as recombination. The sound waves were effectively frozen in place at this point, leaving behind a characteristic pattern of density fluctuations that would later influence the formation of galaxies. These density fluctuations are known as baryon acoustic oscillations, and they have left a subtle but measurable imprint on the large-scale distribution of galaxies. BAOs create a preferred scale in the universe, corresponding to the distance that the sound waves traveled before recombination, about 500 million light-years. This scale acts as a standard ruler that can be used to measure distances in the universe and study its expansion over time. The study of BAOs has become a crucial tool in cosmology, providing independent evidence for the existence of dark energy, the mysterious force driving the accelerated expansion of the universe. By comparing the observed BAO scale at different redshifts, distances, with theoretical models, cosmologists can infer the rate of expansion of the universe and test different models of dark energy. However, while BAOs have proven to be an invaluable tool for studying the universe, there are still unexplained variations in the patterns of these oscillations that have puzzled scientists. In some cases, the observed distribution of galaxies does not match the predictions made by the standard cosmological model. These discrepancies could be due to a variety of factors, including the complex dynamics of galaxy formation, the influence of dark matter and dark energy, or even the limitations of current observational techniques. One possibility is that the variations in BAO patterns are related to the distribution of dark matter, which is thought to make up about 85% of the matter in the universe. Dark matter does not interact with light, making it invisible to telescopes, but it exerts a gravitational influence on visible matter, shaping the distribution of galaxies. If the distribution of dark matter is more clumpy or uneven than expected, it could lead to variations in the BAO patterns that we observe. Another possibility is that the discrepancies are related to the effects of cosmic inflation, the rapid expansion of the universe that occurred in the first fractions of a second after the Big Bang. Inflation is thought to have smoothed out the initial density fluctuations in the universe, but it may have also introduced subtle variations in the distribution of matter that could influence the BAO patterns. Understanding these variations could provide new insights into the nature of inflation and the processes that governed the early universe. The study of BAOs is a rapidly evolving field, with new data and more precise measurements continually being added to the picture. Large-scale surveys, such as the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have mapped the distribution of millions of galaxies, providing detailed information about the BAO scale and its evolution over time. Future surveys, such as the Euclid mission and the Large Synoptic Survey Telescope, LSST, promise to provide even more precise measurements, potentially shedding light on the unexplained variations in BEO patterns. The unknown in the deep space. Gamma-ray bursts, GRBs, are brief yet extraordinarily powerful explosions that, for a few seconds, can outshine entire galaxies. Equally puzzling is the phenomenon of disappearing galaxies, distant cosmic islands that seem to vanish from view, leaving astronomers grappling with possible explanations. These occurrences challenge our understanding of the cosmos, offering glimpses into the unknown and the complex forces at play in the farthest reaches of space. Gamma-ray bursts are among the most energetic events in the universe, releasing more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifetime. First discovered in the late 1960s by the Vela satellites, which were originally designed to detect nuclear explosions on Earth, GRBs have since become a focal point of high-energy astrophysics. These bursts of gamma rays, the most energetic form of light, are detected from random directions in the sky and appear without warning, lasting anywhere from a fraction of a second to several minutes. Despite decades of study, many aspects of GRBs, particularly their origins and the mechanisms that produce them, remain subjects of intense debate. GRBs are classified into two main categories based on their duration: long-duration bursts, which last more than 2 seconds, and short-duration bursts, which last less than 2 seconds. The prevailing theory is that these two types of GRBs originate from different astrophysical events. Long-duration GRBs are thought to be associated with the deaths of massive stars in distant galaxies. When such a star exhausts its nuclear fuel, its core collapses into a black hole or neutron star, while the outer layers are ejected in a supernova explosion. In some cases, this collapse can produce jets of material moving at nearly the speed of light, which emit intense gamma rays as they interact with the surrounding material. These jets are believed to be the source of long-duration GRBs. Short-duration GRBs, on the other hand, are thought to result from the collision and merger of two compact objects, such as neutron stars, or a neutron star and a black hole. These mergers, which also produce gravitational waves, are among the most violent events in the universe, releasing vast amounts of energy in the form of gamma rays. The detection of a short GRB in conjunction with a gravitational wave event in 2017 provided strong evidence supporting this theory, marking a significant breakthrough in our understanding of these elusive bursts. Despite these advances, many questions about GRBs remain unanswered. One of the biggest mysteries is the exact mechanism by which these bursts produce such high-energy gamma rays. The conditions required to generate these bursts are extreme, involving the creation of highly relativistic jets in environments with incredibly high densities and magnetic fields. Understanding these conditions and the processes that drive them is a major challenge, requiring sophisticated theoretical models and simulations, as well as continued observations. Another intriguing aspect of GRBs is their connection to the early universe. Because GRBs are so bright, they can be detected from extremely distant galaxies, making them valuable tools for studying the early stages of cosmic history. Some of the most distant GRBs observed to date occurred when the universe was less than 1 billion years old, providing insights into the formation of the first stars and galaxies. However, the exact nature of these early GRBs and their role in the evolution of the universe is still not fully understood. The study of GRBs is also complicated by their fleeting nature. These bursts appear and disappear in a matter of seconds, making them difficult to observe in real time. Astronomers rely on networks of satellites and ground-based telescopes to detect and quickly follow up on GRB events, capturing as much information as possible before the burst fades away. Despite these challenges, each new detection brings us closer to unraveling the mysteries of these powerful explosions and their place in the cosmic landscape. While gamma-ray bursts represent sudden and dramatic events in the universe, the disappearance of galaxies poses a different kind of mystery, one that challenges our understanding of the stability and visibility of cosmic structures over time. In recent years, astronomers have observed instances where distant galaxies, once visible in earlier surveys, appear to have vanished from the sky. This puzzling phenomenon has led to a range of hypotheses, from the effects of gravitational lensing to more exotic possibilities involving unknown cosmic processes. One possible explanation for the disappearance of galaxies is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Gravitational lensing occurs when the light from a distant object, such as a galaxy, is bent and magnified by the gravity of a massive object, like a galaxy cluster, lying between the distant galaxy and the observer. This can create multiple images of the distant galaxy, or it can cause the galaxy to appear brighter or fainter, depending on the alignment of the lensing object. In some cases, gravitational lensing can create what are known as transient lenses, where the alignment between the distant galaxy and the lensing object changes over time. This can cause the lensed galaxy to temporarily brighten and then fade from view as the alignment shifts. Such transient lensing could explain why some galaxies appear to have vanished. What we are seeing is not the disappearance of the galaxy itself, but rather the end of a lensing event that made the galaxy briefly visible. However, gravitational lensing is not the only possible explanation. Another hypothesis involves the intrinsic evolution of galaxies themselves. Galaxies are dynamic systems, with their brightness and structure evolving over billions of years due to factors such as star formation, supernova explosions, and interactions with other galaxies. In some cases, a galaxy might undergo a dramatic transformation, such as a burst of star formation followed by a rapid quenching of that activity, leading to a significant decrease in brightness. This could cause the galaxy to fade to the point where it is no longer detectable by current instruments, giving the appearance that it has disappeared. There is also the possibility that the disappearance of some galaxies could be related to more exotic phenomena, such as the effects of dark matter or dark energy. These mysterious components of the universe, which make up the majority of its mass and energy, could have unforeseen effects on the visibility and stability of galaxies. For example, interactions between dark matter and regular matter could lead to changes in the distribution of stars and gas within a galaxy, potentially altering its brightness or even causing it to break apart over time. The phenomenon of disappearing galaxies raises important questions about the nature of cosmic structures and the forces that govern their evolution. Are these disappearances rare events, or could they be more common than we realize? How do these observations fit into our broader understanding of galaxy formation and evolution? Answering these questions requires continued observations and the development of new models that can account for the range of factors that might influence the visibility of galaxies. The study of disappearing galaxies also highlights the importance of long-term surveys and the need for new observational strategies. As telescopes become more powerful and surveys become more comprehensive, astronomers will be able to track the evolution of galaxies over longer periods and with greater detail. This will help to identify patterns and trends in the behavior of galaxies, potentially revealing new insights into the processes that drive their formation, evolution, and, in some cases, their apparent disappearance. Both gamma-ray bursts and the disappearance of galaxies exemplify the mysteries that await us in the depths of space. These phenomena challenge our understanding of the universe's most extreme environments and the forces that shape its grandest structures. They remind us that, despite the progress we have made in understanding the cosmos, there is still much that remains unknown and that the universe is full of surprises. The Kuiper Cliff. We now encounter a region that continues to intrigue and baffle astronomers, the Kuiper Belt. This distant zone, home to a multitude of icy bodies, dwarf planets, and other remnants from the solar system's formation, presents us with a puzzling feature known as the Kuiper Cliff. This sharp drop-off in the number of objects beyond a certain distance from the Sun defies our expectations and raises questions about the forces that have shaped the outer solar system. The Kuiper Belt was first theorized in the mid-20th century as a possible reservoir for short-period comets that take less than 200 years to orbit the Sun. It wasn't until the 1990s that the first objects within this region, known as Kuiper Belt objects, KBOs, were discovered, confirming the existence of this vast collection of icy bodies beyond Neptune. These objects, which range in size from small asteroid-like bodies to dwarf planets like Pluto and Eris, are thought to be remnants from the early solar system, left over from the time when the planets were forming. The Kuiper Belt is believed to extend from about 30 astronomical units (AU) from the Sun, just beyond the orbit of Neptune, to around 50 AU. For years, astronomers expected that the density of objects would gradually decrease as one moved farther from the Sun, in line with the general distribution of material in the solar system. However, observations have revealed something unexpected. Instead of a gradual decrease, there is a sudden drop in the number of objects beyond approximately 48 AU. This feature, known as the Kuiper Cliff, marks a steep decline in the population of KBOs, and its existence has been difficult to explain. The Kuiper Cliff raises several fundamental questions about the formation and evolution of the outer solar system. One of the primary mysteries is why there appears to be so little material beyond this point. Theories of planetesimal formation, which describe how small bodies coalesce to form larger objects in the early solar system, suggest that the Kuiper Belt should extend well beyond 48 AU. Yet, the observed drop-off in the number of KBOs suggests that something has either prevented objects from forming in this region or has removed them over time. One hypothesis to explain the Kuiper Cliff is that the outer edge of the Kuiper Belt marks the boundary of the solar system's original protoplanetary disk, the disk of gas and dust from which the planets and other solar system bodies formed. If this disk had a sharp outer edge, it could explain why there are fewer objects beyond a certain distance. However, this idea is complicated by the fact that other evidence suggests the protoplanetary disk should have extended much farther into what is now the scattered disk and the Oort cloud, a distant, spherical shell of icy bodies that surrounds the solar system. Another possible explanation for the Kuiper Cliff involves the gravitational influence of the giant planets, particularly Neptune. During the early stages of the solar system's formation, the orbits of the giant planets were likely more dynamic and chaotic than they are today. As these planets migrated to their current positions, their gravitational interactions could have ejected many objects from the outer Kuiper Belt, either sending them into the inner solar system as comets or flinging them into distant orbits in the scattered disk or Oort cloud. This process, known as planetary migration, could have effectively sculpted the Kuiper Belt, creating the observed drop-off in the number of objects beyond 48 AU. However, even planetary migration does not fully account for the sharpness of the Kuiper Cliff. Some astronomers have proposed that an unseen distant planet, sometimes referred to as Planet 9, might be responsible for the cliff. If such a planet exists and orbits the Sun at a great distance, its gravity could have perturbed the orbits of KBOs in the outer Kuiper Belt, either ejecting them from the solar system entirely or drawing them into new orbits that place them beyond the observable region. This idea is closely related to the ongoing search for Planet 9, which, if confirmed, could provide important clues about the structure and history of the Kuiper Belt. Another intriguing possibility is that the Kuiper Cliff could be the result of interactions with the galactic environment. As the solar system orbits the center of the Milky Way galaxy, it passes through regions of varying density, including molecular clouds, stellar clusters, and spiral arms. These encounters could have had a significant impact on the outer solar system, particularly in its early history, when the Kuiper Belt was still forming. Gravitational interactions with nearby stars, or the passage through dense interstellar clouds, could have stripped material from the outer Kuiper Belt, leading to the observed drop-off in the number of objects. The Kuiper Cliff also raises questions about the nature and distribution of objects in the more distant regions of the solar system, particularly in the scattered disk and the Oort cloud. While these regions are much farther from the Sun and more sparsely populated than the Kuiper Belt, they are believed to contain a significant number of icy bodies, some of which may be the source of long-period comets that occasionally visit the inner solar system. Understanding the relationship between the Kuiper Belt and these more distant regions is crucial for building a complete picture of the solar system's structure and evolution. The mystery of the Kuiper Cliff is further complicated by the limitations of current observational technology. The objects in the Kuiper Belt are small, dark, and distant, making them difficult to detect even with the most powerful telescopes. As a result, our knowledge of the Kuiper Belt and its population is still incomplete, and there may be many more objects lurking beyond the cliff that have yet to be discovered. Future missions, such as the proposed James Webb Space Telescope, JWST, and other next-generation observatories, will be essential for probing the outer reaches of the solar system and shedding light on the true nature of the Kuiper Cliff. The Kuiper Cliff remains one of the most intriguing and perplexing features of the solar system, challenging our understanding of how the outer regions of the solar system formed and evolved. It is a reminder that, despite the progress we have made in exploring our cosmic neighborhood, there are still many unanswered questions and unexplored frontiers. The study of the Kuiper Belt and its mysterious cliff is not just about understanding a specific region of the solar system. It is about uncovering the processes that have shaped the solar system as a whole and the forces that continue to influence it today. The Fermi Paradox. Amidst the myriad of unsolved mysteries that the universe presents, one question has captivated human imagination for decades: the Fermi Paradox. This paradox, named after the renowned physicist Enrico Fermi, centers around a simple yet profound question. If intelligent extraterrestrial civilizations exist elsewhere in the universe, then where is everybody? The paradox highlights the apparent contradiction between the high probability of extraterrestrial life, given the vast number of stars and planets, and the lack of evidence for or contact with such civilizations. The universe is staggeringly vast, with an estimated 100 billion galaxies, each containing hundreds of billions of stars. Many of these stars are orbited by planets, some of which reside in the so-called habitable zone, where conditions could be right for life as we know it. Given these numbers, it seems statistically likely that life, including intelligent life, should have arisen elsewhere in the universe. This assumption is bolstered by the discovery of extremophiles, organisms that thrive in harsh environments on Earth, suggesting that life might find a way to exist in a wide range of conditions across the cosmos. Despite this, the silence from the cosmos has been deafening. We have found no clear signs of extraterrestrial life, no evidence of advanced civilizations, and no communication from the stars. This absence of evidence is what makes the Fermi Paradox so perplexing. The paradox emerges from the expectation that if intelligent civilizations were out there, they should have made themselves known by now, either through detectable signals, evidence of space travel, or other observable phenomena. Yet, as far as our observations go, the universe appears to be empty, at least in terms of intelligent life. There are numerous hypotheses that have been proposed to explain the Fermi Paradox, each reflecting different aspects of the challenges inherent in finding extraterrestrial intelligence. One of the simplest explanations is that intelligent life is exceedingly rare. While the conditions for life may exist in many places, the emergence of intelligent, technologically capable civilizations might be an extraordinarily rare event. Life could be common in the universe, but intelligent life might be vanishingly rare. Or it could be that civilizations capable of communication are a fleeting phase in a planet's history, extinguished before they can reach out to the stars. Another possibility is that intelligent civilizations do exist, but they are too far away for us to detect. The vast distances between stars and galaxies mean that even if a civilization were sending out signals, those signals might take thousands or even millions of years to reach us, and vice versa. Furthermore, the signals might degrade over time and distance, becoming indistinguishable from the cosmic background noise by the time they arrive. The sheer scale of the universe could mean that civilizations are spread so far apart that they remain effectively isolated from each other. A related idea is that we might be looking for the wrong signs of intelligence. Our search for extraterrestrial life has largely focused on detecting radio signals or other forms of electromagnetic communication, but advanced civilizations might use technologies that are beyond our current understanding or detection capabilities. They could be communicating in ways that we cannot yet perceive, or they might have developed methods of communication that do not rely on electromagnetic waves at all. This raises the possibility that intelligent civilizations could be out there, but we simply lack the means to recognize their presence. Another intriguing hypothesis is that advanced civilizations might deliberately avoid contact with us. This idea, sometimes referred to as the zoo hypothesis, suggests that extraterrestrial civilizations are aware of us, but have chosen not to interact, perhaps to allow humanity to develop independently. They might see us as too primitive or unworthy of contact, or they could have ethical reasons for maintaining their distance. In this scenario, the lack of evidence for extraterrestrial life is not due to their absence, but rather a result of their deliberate decision to remain hidden. Alternatively, it is possible that civilizations self-destruct before they reach the stage of interstellar communication. This idea, often referred to as the Great Filter, posits that there is a critical barrier or set of barriers that prevent civilizations from surviving long enough to make contact with others. The Great Filter could be a natural disaster, such as a supernova or gamma-ray burst, or it could be a self-inflicted catastrophe, such as nuclear war, environmental collapse, or runaway artificial intelligence. If the Great Filter exists, it might explain why we have not detected any signs of advanced civilizations. They simply do not survive long enough to become detectable. The Fermi paradox also raises the possibility that intelligent civilizations might not be interested in exploring or colonizing the galaxy. They might be content to remain on their home planets, having no desire or need to expand beyond their immediate environment. This could be due to philosophical, cultural, or practical reasons. Perhaps they have reached a level of technological or social development where they see no benefit in spreading across the stars, or they might have found ways to fulfill their needs without leaving their homeworlds. Another consideration is that the universe might be teeming with life, but most of it is microbial or at a level of intelligence that does not lead to technological advancement. The majority of life forms might be simple organisms that do not communicate in ways we can detect. Even on Earth, most life is microbial, and complex life forms capable of technology represent a tiny fraction of the biosphere. This raises the possibility that intelligent life is just one small branch on the vast tree of life, and most of the universe's life forms are invisible to us because they do not emit detectable signals. The Fermi paradox also invites us to consider the possibility that we are the first, or one of the first, intelligent civilizations to arise in the universe. If intelligence is a relatively new phenomenon in cosmic history, we might simply be the first to reach a stage where we can ask these questions and search for others. In this case, the silence we observe might be the result of the universe being in its early stages of developing intelligent life, with more civilizations potentially arising in the future. The search for answers to the Fermi paradox continues to drive research in astrobiology, astronomy, and the search for extraterrestrial intelligence, SETI. Scientists are exploring new ways to detect signs of life, from analyzing the atmospheres of exoplanets for biosignatures to searching for technosignatures, indications of advanced technology that might be visible from Earth. As our technology improves and our understanding of the universe deepens, we may eventually find evidence that answers the question posed by Enrico Fermi. The Fermi paradox touches on some of the most profound questions we can ask. Are we alone in the universe? If not, where are the others? And what does their absence mean for us? These questions are not just scientific, but also philosophical, challenging us to think about our place in the cosmos and the nature of life itself. Whether we find evidence of extraterrestrial civilizations or continue to search in silence, the Fermi paradox will remain one of the most compelling and mysterious questions in the exploration of the universe.